This is a really fun problem. It tells us that a certain first order reaction, and that is actually key, has a rate constant of 2.75 times 10 to the negative 2 inverse seconds at 20 degrees C. So I'm going to write down 20 degrees C right here, just so that we know that this is the rate constant at 20 degrees C, and we don't get it mixed up with the rate constant at a different temperature. It then asks me what the rate constant would be at 60 degrees C if the activation energy for this is equal to 75.5 kJs per mole. I have to remember from an earlier equation that I will link to right here that for a first order reaction, the natural log of K1 divided by K2 is equal to the activation energy divided by the ideal gas constant multiplied by this big crazy thing, 1 over T2 minus 1 over T1, and that's the equation. So I have K1, that's 20 degrees C. K2 is what I'm trying to solve for. I also have the activation energy. The ideal gas constant for one of these kinds of reactions has to be 8.314 joules per mole Kelvin. Now I realize there are different forms of the ideal gas constant. When you're doing this or using this equation, you have to use that ideal gas constant. Once again, T2 is equal to 60 degrees Celsius, and T1 is equal to 20 degrees Celsius. In order to make sure your units are consistent, however, you'll have to convert to kelvins. 60 degrees Celsius, adding 273.15 to it, is equal to 333.15 kelvins. And 20 degrees Celsius is equal to 293.15 kelvins. So I have T1, I've got T2, I've got the ideal gas constant, I have my activation energy, I have the I have K1, I'm trying to solve for K2. This is pretty much at this point just an algebra problem where I have to get K2 on one side of the equation and everything else on the other. I realize it's a lot of numbers, but we can go ahead and do that. So I'm going to go ahead and remember from my basic algebra that if you have the ln or natural log of one number divided by another number, it's the same thing as having the natural log of the numerator minus the natural log of the denominator. So I can go ahead and separate that out or rewrite this as this. Hopefully you're okay with that. I then throw in my numbers. Activation energy 75.5 kJs per mole. My ideal gas constant, and in fact, in order to make my units a match, because I've got joules over here for R and I've got kilojoules over here, I need my units to match. So I'm going to have to change this to joules instead of kilojoules, or I could go vice versa, but I think it'd be easier this way. If I take this, multiply it by 1,000, that's 75,500 joules per mole, and hopefully we're okay with that. So I'm going to go ahead and do that. 75,500 joules per mole. I'll divide that by the ideal gas constant, 8.314 joules per mole Kelvin. And then I multiply it by 1 divided by T2, which is 333.15 kelvins, minus 1 over T1, which is 293.15 kelvins. The moles, you'll notice, cancel each other out, and the joules cancel each other out. The kelvins also will eventually cancel each other out once I'm all done doing the multiplication. Now I did that in my calculator. What I ended up getting was negative 3.72 for all of this stuff here on the right side. You can double check that on your calculator. If I throw in, by the way, the ln, or K1, sorry, is good grief. Yeah, I'll just keep this, I guess, as ln of K1. ln of K1, K1 is 2.75 times 10 to the negative 2 inverse seconds. So I've got the ln of K1 minus the ln of K2, and K2 is the mystery thing, right? I throw this into my calculator, and I end up getting negative 3.59 inverse seconds, minus the ln of K2 equals negative 3.72. I think it's assumed that we're going to ignore the units on this one. Maybe that's a questionable behavior, but I'm okay with it. So what I'm going to need to do is use algebra to get the ln of K2 on one side and everything else on the other. So I have to add 3.59 to both sides, and I have to multiply both sides by a negative 1 in order to make this positive. When I do that, I end up getting the ln of K2 is equal to 0.129. I now have to solve for K2, and the way you do that is by taking e, which is the anti-natural log, I don't know what the heck it's called, some algebra thing. You can do it on your calculator. If you take e and raise it to the power of both sides, the natural log and e cancel each other out. You end up with k2 equaling e to the negative 0.129. When I do that, I end up getting 1.13. I'll go ahead and throw down my units at the bottom. Inverse seconds. That is the correct answer to this question.